this video is a continuation of the previous video that we have about graphing rational functions. So there will be more graphing of rational functions here. So to continue, may I proceed to example 6. So what is the graph of the rational function 2 times 3x plus 12 times x minus 2 divided by x minus 1 times x plus 5 here. So again, looking at this factored form of our rational functions, we cannot find any common factor between the numerator and the denominator. So then, therefore, there is no point of discontinuity here except at the vertical asymptotes. So let's proceed to our y-intercept here. And our y-intercept can be obtained when you want to evaluate the function at x equals 0. So what is f of 0? So evaluating this one, we just substitute the value of our x, which is 0, to the function. So this is 2 times 3 times 0 plus 12 times 0 minus 2. And this will be divided by 0 minus 1 times 0 plus 5. And we have f of 0, this one, 2 times 12 here, because 3 times 0 is 0 and 0 plus 12 is 12, times negative 2, because 0 minus 2 it's minus 2, and this will be divided by negative 1 times 5, which is negative 5. So 2 times 12 is 24, and 24 times negative 2, that is negative 48 here. And this will be divided by negative 5. And if you have your calculator, that is equal to the decimal 9.6. So therefore, our y-intercept is at the point 0, 9.6. So this is now our y-intercept. Let's proceed to our x-intercept, if there's any, for this function. Our x-intercept, remember, can be obtained when you set your numerator, the polynomial in the numerator, to 0. And our numerator is 2 times 3x plus 12 times x minus 2, and this will be equal to 0. So setting each factor to 0, we have 3x plus 12, which is equal to 0, and x minus 2, which is also equal to 0. So 3x is equal to the negative 12, because if I subtract 12 to both sides, the 12 here will be cancelled. So that is 3x equals negative 12. And dividing both sides by 3, we have x equals negative 4. And also, this one, x is equal to 2. So our x-intercepts here are negative 4, 0, and 2, 0. The y-coordinates are 0 because these are x-intercepts. And at the x-intercepts, the y-coordinates must be 0. So we have 2 x-intercepts here. So next, we will find the vertical asymptotes. So how do you find the vertical asymptotes? Remember, this can be found when you set denominator equal to 0, because the function must not be defined at that values of x. So our denominator here is x minus 1 times x plus 5, and this will be equal to 0. So x minus 1 is equal to 0, and x plus 5 is equal to 0. Then therefore, our vertical asymptotes here are x is equal to 1 when I add both sides of the equation by 1. And also x is equal to negative 5. So these are our vertical asymptotes in this rational function. Now let's proceed to our horizontal asymptotes. Now to find the horizontal asymptote is to compare the degree of the numerator and the degree of the denominator. And looking at this function here, if you multiply our numerator here, 3x times x, that is 3x squared. And when you multiply it by 2, that is 6x squared. Plus something, but I don't care what is that something because I want just to know the degree of the numerator. And also the denominator, x times x, that is x squared. Plus something, but I don't care with the something because I am after with the degree of the denominator. And looking at this function, the degrees of the numerator and the denominator are equal. So we say that since the degree of the numerator and the degree of the denominator are equal, then our horizontal asymptote is the quotient between their leading coefficients. So this is 6 divided by 1. It's because the coefficient of the leading term in the numerator it's 6, and the coefficient of the leading term in the denominator it's understood to have a coefficient of 1. So that is 6 divided by 1, or that is y is equal to 6. And this is our horizontal asymptote. So with this information, we can now initially plot our graph. So let us now plot the points of interest here. First, our y-intercept is at the point 0, 9.6. So 1, 2, 3, 4, 5, 6, 7, 8, 9.6. It's here. So this is the point 0, 9.6. So our x-intercepts, we have two. The first one is negative 4, 0, negative 1, negative 2, negative 3, negative 4, 0 here. And the other one is 2, 0. So it's here. And we can also plot our vertical asymptotes. And our vertical asymptotes happens to be at x equals 1. So it's here. X equals 1. And also, we have at x equals negative 5. So negative 1, negative 2, negative 3, negative 4, negative 5. So here is our other vertical asymptote. And also our horizontal asymptote is y equals 6. 1, 2, 3, 4, 5, 6. So it's here. So this is our horizontal asymptote. So in order for us to have a good picture of the behavior of the function, let's plot some additional points here. So let's have our table of values. So if this is our x, this is our f of x. So let's plot some points near the points of interest. So first, I want to see where is the graph when x is equal to negative 1. So here, so that I would know the behavior of the function, whether it's like that or it's like this, I don't know. So let's try negative 1. And substituting negative 1 there, so that is 2 times negative 3, because 3 times negative 1, that's negative 3, plus 12 times negative 1 minus 2, that is minus 3, over the value of negative 1 minus 1, that is minus 2, and negative 1 plus 5 is 4. So this is equal to 2 times negative 3 plus 12, and 12 minus 3, it's 9. So 9 times 2, it's 18. And 18 times the negative 3, it's negative 54. And this will be divided by the negative 8. So if you have your calculator, this is equal to 6.75. So plotting this one at x equals negative 1, that is 6.75. So 1, 2, 3, 4, 5, 6.75. So the point is here. Now I want to see also what happens to the graph at x equals negative 3. So I want to see that. So substituting that one there, so 2 times 3 times the negative 3, it's negative 9. And negative 9 plus 12, that is 3. And negative 3 minus 2, that is negative 5. Divided by negative 3 minus 1, that is negative 4. And negative 3 plus 5, that is 2. So we have 2 times 3, it's 6. And 6 times the negative 5, it's negative 30. And this will be divided by negative 8, because negative 4 times 2, it's negative 8. And negative divided by negative, it's positive. And if you have your calculator, 30 divided by 8 is 3.75. So plotting here, negative 1, negative 2, negative 3. But the y is positive 3.75. 1, 2, 3.75. So it's here. Now, I can understand that if I connect this point, I realize that you form a smooth curve here. So this curve is approaching this vertical asymptote, and the other direction is also approaching this second vertical asymptote. So I want to find also the behavior of the function to the right of this point, which is the x-intercept. So let's try when x is equal to 3. So that is 2 times 3 times 3, that's 9. And 9 plus 12, that is 21. So we have also 3 minus 2, which is 1. And in the denominator, that is 3 minus 1, which is 2. And 3 plus 5 equals 8. So if you multiply the numerator, that is 42 over 16. And if you have your calculator, that is equal to 2.625. So plotting here, when your x is 3, so 1, 2, 3, your y is 2.625. 1, 2, 3, but it's only 2.625, this one. And again, I want to see when x equals 6. Let's try here, something here. When x equals 6, so 3 times 6, that's 18. And 18 plus 12, it's 30. And that will be multiplied by 2. So 2 times 30. And when your x is 6, 6 minus 2, that's 4. And this will be divided by 6 minus 1, which is 5. And 6 plus 5 is 11. So we have 2 times 30, it's 60. And 60 times 4, that is 240. And this will be divided by 55. And if you have your calculator, this is approximately equal to 4.36. So when your x is 6, 1, 2, 3, 4, 5, 6, your y, it's 4.36. 1, 2, 3, 4.36. So it's here. So I understand that if I connect these points, I form a curve that is approaching this horizontal line, because this is our horizontal asymptote, and also it's approaching to this line, this vertical line, because this is our vertical asymptote. So the graph is below this horizontal line and not above. Now let's Also, see what's the graph here at the left of this vertical asymptote, whether it's down here or it's up there. So let's try some values, say negative 1, negative 2, negative 3, negative 4, negative 5, negative 6 here. And substituting the negative 6 there, so that is 2 times the negative 6 times 3, that is negative 18, and plus 12, that is negative 6. So substituting negative 6 there, 3 times negative 6, that's negative 18, plus 12, that is negative 6. And negative 6 minus 2, that is negative 8. And this will be divided by negative 6 minus 1, that is the negative 7. And negative 6 plus 5, that is negative 1. So multiplying this one, negative 6 times negative 8, that is positive 48. And positive 48 times 2, that is positive 96. Divided by 7. Because negative 7 times negative 1, that's positive 7. And if you have your calculator, this is approximately equal to 13.71 here. So when your x is negative 6, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, your y is positive 13.71. So let's approximate it's here. Then therefore, the function is not below this horizontal asymptote, but it's above. So I can decipher that the graph is like this. It's approaching this vertical line because this is our vertical asymptote, and it's also approaching to this horizontal line y equals 6 because this is our horizontal asymptote. And remember, there is no point of discontinuity except at the vertical asymptotes. So what is the domain of the function? The domain of the function is the saddable x such that x is a real number and x must not be equal to the negative 5, and also x must not be equal to 1 because these are the values of x which we can find our vertical asymptotes, and our function is not defined at these values of x because these are our vertical asymptotes. So what is our range of the function? Our range is the saddable y such that y is a real number, which means that the function can be seen in all y's there. Although this is our horizontal asymptotes, but this graph crosses at this point here. Now let's proceed to our example number 7 here. What is the graph of our rational function f of x, which is equal to 8 minus 2x squared over 8x plus 4x squared plus 3 here? So as we can recall, based from our guidelines in graphing rational functions, we need to first find any point of discontinuity here. So to find any point of discontinuity is to look for the common factor between the numerator and the denominator here. And the common factor of our numerator is 2, so we have here 4 minus x squared. And also our denominator, the common factor is 4x. So 8x divided by 4x is 2, and 4x squared divided by 4x is x, so plus x. And remember, this is added to a constant of 3. But we can still factor the numerator here, which is a difference of 2 squares. So we have 2 minus x times 2 plus x here. And this is divided by 4x times 2 plus x there. But remember, we have an additional constant of 3. So we can cancel our 2 plus x here. So what will remain is just 2 times 2 minus x divided by 4x. and this is added to a constant of 3. But there is a condition that our x must not be equal to negative 2, because that is our point of discontinuity here. So writing our point of discontinuity, our point of discontinuity is at x equals negative 2. So when your x is equal to negative 2, then you can solve for y, even if this point is not on the graph. 2 times 2 minus the negative 2, so that is 2 plus 2 here, and divided by 4 times the negative 2. And remember, this is added to a constant of 3. So this is 2 plus 2, which is 4, and 4 times 2, it's 8. And 8 divided by negative 8, it's negative 1 plus 3. Then therefore, our y is 2. So the point of discontinuity is at the point negative 2, 2. So this is a hole in the graph. So this is our hole in the graph. So now let's proceed to the y-intercept. Now again, to find the y-intercept is to evaluate the function at x is equal to 0, because at the y-intercept, x is equal to 0. So evaluating the function at x is equal to 0, we have f of 0, which is equal to 2 times 2 minus 0 here over 4 times 0 and plus the constant of 3. But 2 minus 0 is 2, and 2 times 2 equals 4, and 4 will be divided by 0, which is not possible in mathematics. So therefore, we don't have y-intercept. So here we'll write no y-intercept. Now let's proceed to the x-intercept. And to find the x-intercept is to set our numerator to 0. Because at the x-intercept, the y is 0. So our f of x is 0 times any denominator that's 0. So 0 is equal to the numerator. So we'll use the simplified form, which is this one here. So 2 times 2 minus x, which is divided by 4x, but there is a constant of 3. So combining this one into one fraction, we have 4x, and this is 4x divided by 4x is 1 times the numerator, so that is just the same, and 4x divided by 1, it's 4x times 3, so that's 3 times 4x there. So this is 4 minus 2x if I distribute 2 here. So 2 times 2 is 4, 2 times negative x, that's minus 2x, and plus 12x divided by 4x. But here we need to set just the numerator. So we say that our numerator is 10x plus 4. Why? Because 12x minus 2x is 10x, and we still have 4 here. So 10x plus 4 is our numerator, and this is equated to 0. So 10x is equal to the negative 4. So dividing both sides by 10, we have x is equal to the negative 4 over 10. Or you can reduce this as x is equal to the negative 2/5 here. So we have one x-intercept here, which is negative 2/5, 0. So this is our x-intercept. Now let's proceed to our vertical asymptote here. our vertical asymptote here can be obtained when you set the denominator equal to 0. So our denominator, as you can see, it's 4x. So 4x is equal to 0. That's our denominator here. So dividing both sides of the equation by 4, we have x is equal to 0. So this is our vertical asymptote here. And also for our horizontal asymptote, we need just to compare the degree of the numerator by the degree of the denominator. So since our function, which is this one, f of x, which is equal to 10x plus 4 over 4x, this one here, but there is a little condition that x must not be equal to the negative 2. Now looking at the degree of the numerator and the degree of the denominator, they are just equal. So the degrees are the same. And since the degrees of the numerator and the denominator are equal, then we can find our horizontal asymptote by taking the coefficient of the leading term, which is 10, and also the coefficient of the leading term, which is 4. So actually, if you reduce, that is y is equal to 5 halves. And this is also our horizontal asymptote for the function given. So we can initially sketch the graph of our function here. Now we can plot the points of interest here, say the point of discontinuity at the point negative 2, 2. So negative 1, negative 2, 2. So the point of discontinuity is here. And that is the hole in the function. So let's plot also the x-intercept because we don't have the y-intercept. And we have one x-intercept here, which is at x is equal to negative 2/5 here. And also we can plot our vertical asymptote, which is the y-axis, x equals 0, or in other words, the y-axis is our vertical asymptote here. And also we can plot our horizontal asymptote, which is y equals 5 halves or 2.5. So 1, 2.5. So it's here. And to get a full grasp of the behavior of the function, we need to plot additional points here. So plotting additional points. So say if this is our x, this is our f of x. So when your x is 1, where is now the function? So substituting this 1 to our function, which is 2 times 2 minus 1 over 4 times 1 plus the constant of 3. So this is 2 minus 1, which is 1, and 1 times 2, that is 2, over 4 plus the constant of 3. So this is actually 3 and 1/2 or 3.5. So if you plot at x equals 1, that is 3.5. So 1, 2, 3.5. So it's here. And when your x is 4, so substituting it there, 2 times 2 minus 4 over 4 times 4. Added to a constant of 3, we have 2 minus 4, it's negative 2, and negative 2 times 2, that is negative 4 over 16 plus the constant of 3. So this is now 3 minus 1/4. And 3 minus 1/4, it's 2.75 in decimal. So when your x is 4, 1, 2, 3, 4, your y is 2.75. So 1, 2, but at the horizontal asymptote that is 2.5, but our point is 2.75, so it's here. So we understand that at the right of this vertical asymptote, the graph is above this horizontal asymptote there. So you can connect this one and form a curve like that. And we understand that the graph at the left of this vertical asymptote is below this horizontal asymptote because we have a point here, and if you connect, you form a graph like this. So this is our hole, which is at the point -2, 2. So that's the graph of this very beautiful function. So now we can find the domain of the function. So the domain of the function is the set of all x such that x is a real number and x must not be equal to the -2 because that is the point of discontinuity of the function. And also x is not also defined at 0. And for the range is the set of all y such that y is a real number but y cannot be equal to 5/2 because y equals 5/2 is our horizontal asymptote, and y also cannot be equal to 2 because that is a point of discontinuity in this function. So the function is not defined at y equals 5/2 and y equals 2. At this point, let's proceed to example number 8. So what is the graph of this rational function f of x, which is equal to x cubed plus x squared minus 3x minus 2 divided by x squared minus 4. So following the guidelines in sketching the graph of a rational function, we may first find the points of discontinuity of the graph. Now, to find the points of discontinuity is to look for the common factors between the numerator and the denominator here. So factoring the numerator, we have x plus 2 times the trinomial x squared minus x minus 1. And you can check that when you multiply this trinomial by this binomial, this will come out. And also the denominator is a difference of 2 squares, so the factors are x plus 2 times x minus 2. And you can check that when you multiply these two binomials, the product is this one. And as you can see, there is a common factor between the numerator and the denominator, which is this one. So the reduced form of our function is the x squared minus x minus 1 divided by x minus 2. But there is an additional condition that x must not be equal to -2 because we canceled out the common factor, which is x plus 2. And if you equate this factor to 0, x is equal to -2. So 2 is the value of x that makes the denominator 0. Now, division of 0 here is not allowed, so that's why we add an additional condition that x must not be equal to -2. And because we have the cancelled factor, that value of x is the x-coordinate of our point of discontinuity. So looking for the value of y, we have if x is equal to -2, then we can find the value of y. Although this point is not found in the graph of this rational function, but we need to find the coordinates of this point so that we would know what is the whole of the function. So substituting this one here, we have -2 quantity squared minus the negative 2, and we have minus 1 over the negative 2 minus 2. So actually this is equal to 4 plus 2, because minus of the negative 2 is plus 2. So 4 plus 2 equals 6, and 6 minus 1 equals 5. And this is divided by negative 4. And you can check your calculator that this is equal to negative 1.25, or in other words, that's negative 1 and 1/4. So our point of discontinuity is at the point negative 2, negative 5/4 here. So this is the hole in the graph of our function. So next, let us find the y-intercept of the graph, if there's any. And to find the y-intercept is to evaluate the value of the function when x is equal to 0. Because at the y-intercept, the x value is 0. Because that point falls along the y-axis. So substituting this value of x, which is 0, to our function, we have there 0 cubed plus 0 squared minus 3 times 0 minus 2, which is divided by 0 squared minus 4. And you can see that all these three terms goes to nothing, so what will remain in the numerator is just negative 2. And in the denominator also, what will remain is negative 4. And negative divided by negative is positive. So this is positive 1/2. So our y-intercept, there is only one y-intercept, which is 0 1/2. So this is our y-intercept. So let's move on to our x-intercepts. So if there's any here. So how do we get the x-intercepts? We just find the zeros of the polynomial in the numerator. So in other words, we just set our polynomial in the numerator to 0, and we can use the reduced form, which is x squared minus x minus 1. This is the polynomial in the numerator, and we equate this one to 0 just to find the x-intercepts, if there's any. And since this is a quadratic, and I know that the roots are not rational because you find it difficult to factor this one, the factors of negative 1 to get negative x. So we may use the quadratic formula, which asked you to find the value of a, and in this case the a is 1, and the b is negative 1, and also c is negative 1. So looking for the value of x, this is the negative of b. So the negative of the negative 1 plus and minus the square root of b squared, and the square root of negative 1 square minus 4ac, and our a is 1 and our c is negative 1 there, and this is divided by 2a. So 2 times a, which is 1. So our x is equal to the negative of the negative 1, which is 1, plus and minus the square root of 1, because the square of negative 1 is 1, and this is negative 4 times negative 1, that is positive 4. So 4 plus 1 is 5. So that's square root of 5 over 2. So the values of x are 1 minus the square root of 5 over 2, and x is equal to 1 plus square root of 5 over 2. And if you have your calculator, this value of x is equal to the negative of 0.618, and also the other one is 1.618. And of course, these are intercepts. The y coordinates must be 0 here. And so these are our x-intercepts. Next is to find the vertical asymptote of the function. So the vertical asymptote. And to look for the vertical asymptote is to set the denominator equal to 0 here. And our denominator is x minus 2. So we equate this one to 0. So our x is equal to 2. So this is our vertical asymptote. It's a vertical line 2 units from the y-axis. Next is to find also the horizontal asymptote. And to find the horizontal asymptote is to compare the degrees of the polynomials in the numerator and in the denominator. And as you can see, that the numerator is of degree 3. And in the denominator, this is a polynomial of degree 2. So, since the degree of the numerator is greater than the degree of the denominator, then, according to our guidelines, there is no horizontal asymptote in this case. So next is to check whether there is an oblique asymptote. And other authors are saying that this is what we call slant asymptote. And since we observe that the degree of the numerator is greater than the degree of the denominator, and it is 1 degree higher than the degree of the denominator, then this rational function has an oblique asymptote. And how do you find the oblique asymptote? It's just the quotient when you divide the numerator by this denominator. So let us divide the reduced form, the numerator, by the denominator here. So using the long division, we have x squared minus x minus 1 divided by x minus 2. So x squared divided by x, that is x. And x times x, that is x squared. And x times negative 2, that is minus 2x. And then we subtract. So x squared minus x squared is nothing. And negative x minus the negative 2x, that is the same as negative x plus 2x. So the result is x. And then we bring down the last term, which is negative 1. So x divided by x is 1 here. And then 1 times x, that is x. And 1 times negative 2, that is minus 2. And then we again subtract. So x minus x, that goes to nothing. And then minus 1 minus the negative 2, that is the same as negative 1 plus 2. And the result is positive 1. Thus, we say that when you divide x squared minus x minus 1, when divided by x minus 2, the quotient is x plus 1. And there is a remainder of 1. So this will be divided by the divisor x minus 2. So as you can see that the quotient minus the remainder is this one. Hence, we say that our equation of the oblique asymptote is equal to this quotient x plus 1. So it's a straight line whose y-intercept is 1 and the slope is also 1. So this is our oblique asymptote for this rational function. So we can initially sketch the graph of our function at this time by plotting these points of interest in a rectangular plane. So here, now plotting this point of discontinuity, which is at the point -2, -5/4, so we have -1, -2, and then -5/4. 5/4 is -1 and 1/4, so somewhere here. And then we may plot also our y-intercept, which is at 0, 1/2, so it's here. And also our x-intercepts, which are at the point is -0.6180, is somewhere here. And then the other one is +1.618, so here. Remember, their y coordinates are zeros because these are x-intercepts. So we'll just label this hole in this graph -2 as the x coordinate and -5/4 as the y coordinate. And sketching the vertical asymptote, we have x, which is equal to 2, so it's a vertical line that is 2 units from the y-axis. And then we also plot our oblique asymptote, which is x plus 1. So our y-intercept is 1 here, but our slope is 1, so you may rise 1 and run 1, or you may rise 2 and run 2 here. So connecting this point here, this is our oblique asymptote for the graph. So to have a good picture of how the graph of this rational function behaves, let us plot some additional points. So plotting additional points here, I want to see where is the function at x equals 1. So if your x is 1, what is the value of the function? So substituting this one to the reduced form, that is 1 squared minus 1, and 1 squared is 1, so 1 minus 1 is 0, but I have a -1 in the numerator. And in the denominator, we have 1 minus 2, which is -1. And then -1 divided by -1 is 1. So the point has coordinates of 1, 1. So here is the point. And we can decipher that the graph is like this, using these points and connecting them to form a smooth curve that is approaching this vertical line as the vertical asymptote and approaching this line as our oblique asymptote of the graph. Also, I want to see where is the graph to the right of this vertical asymptote. Is it here or is it here? So when your x is 3, substituting that one to the function, 3 squared is 9, minus 3 is 6, and minus 1 is 5. And then if you substitute this 3 in the denominator, so 3 minus 2 is 1. Therefore, our function is 5 when x is 3. So here when x is 3, it's 5. So 1, 2, 3, 4, and 5. So it's here. And maybe you can have some additional points, say 5. So when x is 5, so that is 5 squared minus 5, and 5 squared is 25, minus 5, it's 20, minus 1, it's 19. There. And this will be divided by 5 minus 2, which is 3. And if you have your calculator, this is approximately equal to 6.33. So when your x is 5, 1, 2, 3, 4, 5, your y is 6.33. So somewhere here. And we understand that the graph of the function is something like this. So it's approaching to this vertical line as the vertical asymptote, and it's also approaching to this line as their oblique asymptote of this graph. So labeling this point here, which is the relative maximum of this curve here, this is 1, 1. As you can see here in our table of values. And also this one is having coordinates of 3, 5, 3, 5, which happens to be the relative minimum of this graph here. So with this graph, we can identify the domain of the function. So the domain of the function is the set of all x such that x is a real number, but x cannot be equal to -2, and also cannot be equal to 2, because at -2, that is the point of discontinuity for this rational function, and at x equals 2, that is where we can find our vertical asymptote. And also we can find the range of the function, that the range of the function is the set of all y such that y is a real number, such that y is greater than or equal to 5. Why? Because you can find the function from 5 and above. There is no graph below 5, but there is a graph from 1 and below. So y also is less than or equal to 1. So the function cannot be found above 1 and below 5. So here, let's proceed to example number 9. What is the graph of the rational function which is equal to x squared minus 2x plus 1 divided by x minus 3 and minus 5 here. So to sketch the graph of this rational function, we need to follow the guidelines of how to sketch the graph of a rational function, which I discussed in the previous video. So first, let us find out the point of discontinuity of this function, if there's any. Now to find if there's a point of discontinuity is to find whether it has a common factor between the numerator and the denominator. And to know whether there is a common factor is to combine this fraction with this whole number. So we have x squared minus 2x plus 1, and you know our LCD is x minus 3, so that's the fraction. And since this is a constant, it's understood to have a denominator of 1. So x minus 3 divided by 1 is x minus 3. And that x minus 3 will be multiplied to the -5. So simplifying this function, we have here x squared minus 7x. Why? Because if you distribute -5 to x, that is -5x, and we have here minus 2x. So minus 2x minus 5x, that is minus 7x. And then we distribute also -5 to -3, and the product is positive 15 plus 1, that becomes positive 16 over x minus 3. And looking at this quadratic trinomial in the numerator, we can check that we cannot have a factor of x minus 3, which is our denominator. So in other words, there is no common factor between the numerator and the denominator. And since there is no common factor, we say that there is no point of discontinuity of the graph of this rational function aside from the vertical asymptotes. So let's proceed to the y-intercept here. So what is the y-intercept of the graph? To find the y-intercept, we know that we need to evaluate the function at 0, because the y-intercept must have an x-coordinate of 0. So evaluating this one, f of 0, we will substitute the 0 to our function. We have 0 squared minus 2 times 0 plus 1 all over 0 minus 3. And remember, there is a minus 5 here. So this is 0 squared minus 2 times 0 is 0. So plus 1, we have a 1 over the negative 3. But remember, there is a minus 5 here. So our f of 0 is equal to the combined form of this fraction and this constant by looking its LCD, least common denominator. So negative 3 divided by negative 3, it's 1 times 1, which is 1. And negative 3 divided by 1, it's negative 3 times negative 5, that is positive 15. So 1 plus 15 is 16 divided by negative 3. And if you have your calculator, this is approximately equal to the negative 5.33, because this is negative 5 and 1/3. So our y-intercept is the point 0, negative 16 over 3. So this is our y-intercept. Now let's proceed to our x-intercept here. So to find the x-intercept is to set our numerator, our polynomial in the numerator, to 0. And using this reduced form, we have x squared minus 7x plus 16. This will be equated to 0, because this is our quadratic trinomial in the numerator, which is the reduced form of this, the combination of this fraction and this constant phi. Now I know that the roots of this quadratic trinomial are not rational numbers, so we may use the quadratic formula. So our a is 1 here, our b is negative 7, and our c is 16. So our value of x is equal to the negative of the negative 7, which is our b. And then plus and minus the square root of b squared, and the square of negative 7, it's 49. Minus 4 times a, which is 1, and c, which is 16. And this will be divided by 2 times a, which is 1. Now, simplifying this expression, we have 7 plus and minus 49 minus 4 times 16. And 4 times 16, it's 64. So, minus 64 here. And this will be divided by 2. So, this is 7 plus and minus 49 minus 64 is negative 15. So this is plus and minus negative 15 divided by 2. And as you can see, that this square root of negative 15 is an imaginary number. And since this is an imaginary number, we cannot see this point in the real plane. So in other words, we say that there is no x-intercept in the graph of this rational function. Now we'll proceed to the vertical asymptote. So to find the vertical asymptote is to set our polynomial in the denominator to 0. And looking at this reduced form, our polynomial in the denominator is x minus 3. So setting this one to 0, we have x equals 3. So this is our vertical asymptote of the graph. Now let's proceed to the horizontal asymptote. To to find the horizontal asymptote is to compare the degree of the numerator with the degree of the denominator. And since our numerator has a degree 2, which is more than the degree of the denominator, then there is no horizontal asymptote. So we write here, since the degree of the numerator, which is 2, is greater than the degree of the denominator, which is 1, then there is no horizontal asymptote. So we can check whether the graph has an oblique asymptote or slant asymptote. Now, looking at the function, the degree of the numerator is 1 degree higher than the denominator. So if the difference of their degrees is 1, then the graph of this rational function has an oblique asymptote. And how do you find the oblique asymptote? We simply divide the numerator by its denominator. So using the reduced form of this function, we divide x squared minus 7x plus 16 by the divisor here, which is x minus 3. So x squared divided by x, it's x. So x times x, that is x squared. And x times the negative 3, that's minus 3x. And subtracting this one, x squared minus x squared is 0. And minus 7x minus the negative 3x is the same as minus 7x plus 3x. And minus 7x plus 3x is minus 4x. And bringing down the next term, which is 16, we can divide minus 4x by x. And the quotient is minus 4. So minus 4 times x, that is minus 4x. And minus 4 times minus 3, that is positive 12. And then subtracting this one again here, so minus 4x minus the negative 4x, that's 0. So 16 minus 12, it's 4. So it has a remainder of 4. So we say that when you divide x squared minus 7x plus 16 by x minus 3, the quotient is x minus 4 with a remainder of 4 here, and this will be divided by x minus 3. Now you see that the quotient is x minus 4 plus the remainder of 4. Hence, using our guidelines, we say that the equation of our oblique asymptote is y equals x minus 4. It's a straight line whose y-intercept is negative 4 and the slope is 1. So using this information, we can initially sketch the graph of our function here. So plotting the points of interest here in the plane, we plot first the y-intercept, which is the point 0, negative 16 over 3. But the y is negative 16 over 3, which is equal to negative 5 and 1/3. So negative 1, negative 2, negative 3, negative 4, negative 5 and 1/3. So the point is here. And also plotting the vertical asymptote, we have x equals 3. It's a vertical line that is 3 units to the right of the y-axis here. And also plotting our oblique asymptote, which is y equals x minus 4, and this line is having a y-intercept of negative 4. So negative 1, negative 2, negative 3, negative 4. And since the slope is 1, you may rise 1 and run 1. Or you may rise 4 and run 4. So the oblique asymptote is a line having a y-intercept of negative 4, but the slope of 1. So with this information, it's very difficult to plot function having only one point and the two asymptotes, the vertical asymptote and the oblique asymptote. So what will you do is to plot additional points so that you can determine the behavior of the function within these two asymptotes. So plotting additional points. So if your x is here, your f of x is also here. So let's try when your x is 1. So when your x is 1, 1 squared minus 7, because 7 times 1 is 7. So plus 16 divided by 1 minus 3. And the value of the function is 1 minus 7, which is negative 6, plus 16. The sum is 10. And 10 divided by negative 2 is equal to the negative 5. So plotting this point, if your x is 1, negative 5. So 1, negative 2, negative 3, negative 4, negative 5 is here. And then we would like to see if your x is 2. If your x is 2, so that is 2 squared, which is 4, minus 7 times 2, which is 14, and plus 16 divided by 2 minus 3. So simplifying this one, 4 minus 14, it's negative 10 plus 16, that is 6. And 6 will be divided by negative 1 because 2 minus 3 is negative 1. So this is negative 6. So plotting the point, when x is 2, it's negative 6, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6 here. So we understand using these 3 points that the graph is like this here. So the curve is approaching this line, which is the oblique asymptote, and also the curve is approaching this line, which is our vertical asymptote. So we would like also to see the function at the right of this vertical asymptote, whether it's here or it's here. So say when x is 4, I want to see when x is 4. So when x is 4, substituting that one there, that is 16 minus 28, because 7 times 4 is 28. And then plus 16 divided by 4 minus 3. So simplifying this one, 16 plus 16, that is 32, and 32 minus 28 is 4. So 4 divided by 1 is 4. So the point is 4, 4. So when x is 4, the y is also 4. 1, 2, 3, and 4 here. And then when your x is 5, so substituting 5 here, so 5 squared is 25 minus 7 times 5, which is 35, plus 16 all over 5 minus 3. And if you simplify 25 minus 35, that is minus 10, and minus 10 plus 16 is 6. And 6 divided by 2 is 3. Positive 3. So when your x is 5, 1, 2, 3, 4, 5, your y is 3. So 1, 2, and 3. It's here. So using this point, we understand that the graph is like this here. So it's approaching this vertical line, because this is our vertical asymptote, and also approaching this slant line, because this is our oblique asymptote. So at this point is the relative minimum of this curve, and it has coordinates of 5, 3. Also, this point is the relative maximum of this curve here, and it has coordinates of 1, negative 5. So we can determine also the domain and the range of the function. Our domain is the set of all x such that x is a real number but x cannot be equal to 3, because this is where we can find our vertical line. Also, the range of the function is the set of all y such that y is a real number but y is greater than or equal to 3, because the function exists from 3 and above, or y is less than or equal to -5. So which means that the function cannot be found when y is below 3 and greater than -5. So let's proceed to our last example here. What is the graph of the function f of x, which is equal to 2x cubed plus 8x divided by 5x minus 5? Now, using the guidelines that I have presented in the previous video, we need to check whether there is a point of discontinuity of the function. Now, how do we know the point of discontinuity? Is to look for the common factor between the numerator and the denominator. So, factoring the numerator, we have a common factor of 2x. So, 2x cubed divided by 2x is x squared. And 8x divided by 2x is positive 4. And also the denominator, we have a common factor of 5. So 5x divided by 5 is x. And minus 5 divided by 5 is minus 1. And looking at this rational, we cannot find any common factor between the numerator and the denominator. So there is no point of discontinuity here. So we may proceed to finding if there is a y-intercept of this graph. And how do you find the y-intercept? By evaluating the function when x is equal to 0. So substituting the value of x to the function, which is 0, we have 2 times 0 cubed here plus 8 times 0 is divided by 5 times 0 minus 5. So simplifying this one, the numerator goes to 0, everything because of the zeros there. And this will be divided by minus 5 because 5 times 0 is 0, but we have here a minus 5. And 0 divided by -5 is 0. So therefore, our y-intercept is at the point of origin, having coordinates of 0, 0. Now, looking for the x-intercept, we need to set the polynomial of our numerator to 0. Now, our numerator is 2x times x squared plus 4, and equating this one to 0, we have 2x is equal to 0. And the other one, x squared plus 4 is equal to 0. So dividing both sides by 2, we have x is equal to 0 because 0 divided by 2 is 0. And also this one, we have x squared, which is equal to the -4. And taking the square root of both sides, we have x is equal to the square root of the -4. And the square root of -4 is positive negative 2i. So 2i and -2i. And since these are imaginary numbers, we cannot find this in the real plane since this is an imaginary number. So we have an x-intercept only when x is 0. So of course, because this is an x-intercept, the y-coordinate must be 0. So this is our x-intercept. So as you can see, our x-intercept and our y-intercept are just the same because this is the point of origin. Now let's proceed to the vertical asymptote here. So how do you find the vertical asymptote? Again, we set the polynomial in the denominator to 0. And since our denominator is 5x minus 5, we equate this one to 0. So 5x is equal to 5. And dividing both sides of the equation by 5, we have here x is equal to 1. And this is our vertical asymptote of this rational function. Now, let's proceed to the horizontal asymptote. Now, to find the horizontal asymptote is to compare the degree of the numerator with the degree of the denominator. And since the degree of the numerator is greater than the degree of the denominator, because our degree in the numerator is 3, compared to the degree of the denominator which is 1, then we say that there is no horizontal asymptote. So, since the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Now that we don't have a horizontal asymptote, we may check whether there is an oblique asymptote here, or the slant asymptote. Now, since the degree of the numerator is 2 more than the degree of the denominator, then there is also no oblique asymptote. So we say here, since the degree of the numerator is not 1 degree higher than the degree of the denominator, then there is no oblique asymptote for this graph. So with this information, we can initially sketch the graph of our function here. Now, plotting the y-intercept, which is the same as the x-intercept, the graph passes through this point, which is the point of origin. And also we can plot the vertical asymptote, which is 1 unit to the right of the y-axis here. And since we don't have the horizontal asymptote and oblique asymptote, then that is the only information we can get from this one. So in order to have a full grasp of the behavior of the function, we may plot some additional points here. When your x is here, your f of x is also here. So let's try some values of x, which is to the left of this x-intercept and at the same time the y-intercept. Say, let's find out where is the graph at x equals -2. So substituting to the function, 2 times -2 is -4. And then -2 squared is 4 plus 4 divided by 5 times -2 minus 1, which is -3. So the value of the function is 8 times the -4, which is -32. And this will be divided by -15. And negative divided by negative is positive. And if you have a calculator, you can check that this is approximately equal to 2.13. So plotting this one, -1, -2, but the y is 2.13. So here, the point is here. You can also check when your x is closer to this vertical asymptote, say 1/2. So when your x is 1/2, 2 times 1/2 is 1. And square of 1/2 is 1/4. So 1/4 plus 4 over 5 times 1/2 minus 1 is negative 1/2. So this is equal to 1/4 plus 4, that is actually 17/4. And this will be multiplied by the reciprocal of the denominator, which is negative 5/2. And the reciprocal of that is negative 2/5. So simplifying this one, this is negative 17/10. And you can check that this is equal in decimal to negative 1.7. So when your x is 1/2, your y is negative 1.7. It's here. So with this information, we can approximate the behavior of the function to be like this. So it tends to approach this vertical line, being the vertical asymptote. But I want to see what is the behavior of the function to the right of this vertical asymptote. So let's try when your x is 2. When your x is 2, 2 times 2 equals 4. And 2 squared is also 4, so plus 4. And this will be divided by 5 times 2 minus 1, which is 1. So simplifying this one using simple arithmetic, that is 4 plus 4 is 8, and 8 times 4 is 32. So 32 divided by 5. And 32 divided by 5, in decimal, this is 6.4. So you can plot this one when your x is 2 here. The y is 6.41, 2, 3, 4, 5, 6.4 is here. Now I want to see some values of x closer to this one, say 1.5 or 3/2. So a 3/2, if you substitute, so 2 times 3/2 is 3. And this will be multiplied by 3/2 squared, which is 9/4 plus 4. And this will be divided by 5 times 3/2 minus 1, which is 1/2. So this is equal to 9/4 plus 4, that is 25/4, but this will be multiplied by 3, that is 75/4. But this will be multiplied by the reciprocal of the denominator, which is 5/2. So the reciprocal of 5/2 is 2/5. So multiplying these two fractions, we may cancel 75 with this 5 here, but we still have here 15. And the 2 here will be cancelled with this one. We have a 2 here. So we have 15/2. Or in other words, that is 7.5. So when your x is 3/2, so here, your y is 7.5. 1, 2, 3, 4, 5, 6, 7.5. It's here. So let's try one more value of x, which is 3. So 2 times 3 is 6. And then 3 squared is 9 plus here the 4. And divided by 5 times 3 minus 1, which is 2. So using simple arithmetic, 9 plus 4 is 13. And 13 times 6 is 78. And this will be divided by 10, because 5 times 2 is 10. So this is in decimal 7.8. So when your x is 3, so 1, 2, 3, your y is 7.8. 1, 2, 3, 4, 5, 6, 7.8 here. So we understand that using these 3 points, the behavior of the function is like this. So this is the graph of this rational function, wherein there is no horizontal asymptote as well as an oblique asymptote. So we can determine also its domain. and the domain of the function is the settable x such that x is a real number and x must not be equal to 1. Because this is where we can find the vertical asymptote. But the range of this function is the set of all y such that y is a real number. Because the function is present in all y's. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.